In this lecture, we will study instrument transformers. First, we will discuss current transformer, then voltage transformer. After that, we will see how to classify various kinds of instrument transformers according to various standards. That is IEC standard or IEEE standards. There is little bit difference between the classification of instrument transformers according to these two kinds of standards. IEEE is usually used in United States of America and IEC is usually found in India and other countries. So let us start the discussion of instrument transformers. So as the name suggests, instrument transformers are also transformers only, so their functioning is similar to that of a transformer. However, they are particularly being used to measure some quantities. Like current transformer is being used to measure the current in the power system, and the voltage transformer is usually used to measure the voltage of the power system. Okay, so as we can see that the level of current and voltage can be very high in a normal power system. Voltage may go up to 765 kV as of now, and currents may be some 1000 ampere. Okay, so the instruments like our meters, relays, and all other associated equipment, they might not be able to work on such high levels. So what we need to step down those signals to appropriate levels so that we can feed them into our equipment like relays, meters, and other items. Okay, similarly, some auxiliary equipment are also being run using the signals received from these instrumentation transformers. Secondly, they are also providing us some kind of safety provision by isolating, having an isolation between the power system level of voltage and currents to the signal level of voltage and currents. So the personnel which is sitting in the substation and working with the various equipment which are connected to instrument transformers is safe. He is not prone to the high levels of voltage and currents of the power system. Okay, so these are some of the requirements. Why do we use instrument transformers? Why cannot we just directly measure any voltage or current and utilize it? So this is one of the thing. Now this current transformer especially can be classified for its purpose, like what purpose it is going to solve, whether we are going to use it for measurement of energy or the current level, or whether this thing is going to feed the current to the relay for its functioning. Like overcurrent relay requires current input for functioning. Similarly, impedance relay also requires the current level at its point to find the impedance by measuring the voltage also. So there are various relays which are going to utilize these signals from the current transformer as well as voltage transformers. Okay, but these two requirements, one for the measurement for like energy reading purpose, metering purpose, actually we call it as metering purpose, and other the protective relay purpose, these two requirements have little bit difference in their necessary conditions. Like usually what we need to do with the metering equipment, we need to measure the levels of current or the energy consumed during steady state of the normal state of the power system. Okay, so the current transformer should be giving us very accurate transformation of current during the normal scenario. Usually normal scenario also takes care of the 20%, about 20% of the overload in the subsystem. Okay, however, these meters which are connected with the CT, they might not be able to work properly, or they may get damaged if higher levels of current which are there during the fault, even after transformation to the secondary side, if they are fed to these meters, they will get damaged. So to avoid that damage, the CT should provide some kind of means to protect the connected equipment during the fault. Okay, so this metering purpose CT is having some different criteria. However, the CT which will be feeding the protective relay it may not give, let us say, 100% exact readings during the normal situation, but it should faithfully transform the currents during the fault so that the relay can come to a decision to trip or not to trip the circuit breaker according to the scenario of the fault. Okay, so this is the another requirement of the protective relay CTs which are going to be supplying the protective relays, that is, they should faithfully work during the fault levels. They may not give exact 100% accurate readings during the normal levels, but the metering purpose CTs, they should give 100% or very accurate results during the normal level, and they should protect the associated equipment or the connected equipment during the fault levels. Okay, so how do we do that? Let us see for the CT. Now, here I am drawing excitation characteristics of two kinds of core material. This is the knee voltage or the knee point, usually around 1.5 Tesla. Okay, this is for CRGO steel, cold roll grain oriented steel. Okay, and another I am going to draw. This is for the nickel iron alloy. Now, you can see that the CT or the transformer which will be made of the CRGO steel will get saturated at a higher level of ampere turns per meter. Okay, however, the CT or the transformer which will be made of this kind of alloy will get saturated at a lower ampere turn per meter or the MMF. Okay, or the excitation current also we can translate it to E and I also, or phi or I also, or this is or I. Okay, so from this thing we can see that the CT which will be manufactured by CRGO steel, okay, it will be able to do its function up to a higher level of current. Okay, however, this CT which will be made of nickel iron alloy will get saturated very fast as compared to the CRGO steel CT. Okay, so you can see that this CT material can be used for making the CTs which are for protection purpose, and this material can be utilized for metering purpose. Similarly, you can see that the linearity equation is comparatively more linear for this kind of CT material during the normal load conditions. Okay, this is usually from, let us say, up to 120% of the full load current. Okay, and this is up to, let us say, more than 50 times, or 150% or higher than that. Okay, so you see that at a lower level of current, this will be more faithful in transforming the current levels, okay, as compared to the CRGO. Now, this is the part in which we have seen various materials for the construction of two kinds of CT. Similarly, when we will study the transient phenomena, we will see that these materials may not be simply enough for our purpose. We might have some kind of other manufacturing style or other kind of design, like we might have to use some air gaps to induce the or introduce the linearity through the air gap. So even if when we use this material, the relay might not be able to get the faithful transformation using this material CT during the transients. Okay, so we may require some special kind of construction. Now we are saying that CT should faithfully transform the various levels of current. What does it mean? It means that there should not be any error. Now what can be the reason of the error? Let us see that thing in the next slide, where we will try to draw the equivalent circuit of a CT, which is just that of a normal transformer only, and we will try to see what is the meaning of error, what we are trying to say here. Okay, usually CTs can have multiple kind of design. One of the design is having CT in the bushing of the transformer. Let us say this is the HV bushing of the transformer. So what we do, this is insulated medium, okay, and the HV conductor is passing inside it. Okay, so what we are doing, we are taking readings through installation of CT into the bushing of the transformer only. Okay, this is the transformer tank. So this is one of the construction available in the substation. Okay, similarly we can have dead tank or the live tank CT also. What does it mean? It means like this is the normal wire of the HV side. Okay, we can have a CT like this. This is insulation and this is tank. This tank might be filled with transformer oil for insulation as well as cooling purpose. Okay, if this tank is earth or it is connected to earth, let us say like this, okay, then it is called dead tank CT. If we have a CT like this, the tank is here, a transformer oil is inside it, and it is standing on some insulation, and this is the floor. Okay, so this is at live, it is not at ground potential, it is at ground potential. So it is live tank CT design. Each kind of CT has some benefits as well as some disadvantages. Okay, so depending upon the utility and the cost involved and the space available, we can opt for any kind of design. So this thing is usually taken care of while designing the system. Okay, now what is the meaning of current transformer if we want to make an equivalent circuit diagram? Usually what we do, we show that the primary is just a single wire, or it may be having some one or two turns also according to the design. But usually what we do, we connect the CT in line with the power system. Okay, this wire itself acts as the primary winding. Okay, and the secondary winding is wound across this wire, and any relay etc. or equipment is connected to its terminal. Now this is only single turn, it's return circuit. Okay, and this is multiple turns. Let us say it is 1:200. Okay, so what will happen? 200 ampere current flowing in this wire will get translated into only 1 ampere current. So in this way, we are going to have transformation of high level of power system current into a lower level of current for the feeding to the relays or metering equipment. Okay, now there will be a question into the minds of student that this number of turn on the secondary side is high and the primary side is low, then the voltage at this secondary side will be higher, that is N1 upon N2 is usually equal to E1 over E2. So people will say that E2 will be equal to E1 into N2 by N1, and N2 is very high as compared to N1, so E2 will be very high. Okay, but you see that the E1 involved, what is the value of this E1? E1 is just the potential drop between this point and this point of the wire or the primary winding. Okay, so the resistance of wire is very low. Okay, so the potential drop across these 2 points or across this length is very low. So E1 is very low actually. So this E1, although this wire with respect to ground can be at, let us say, 765 kV, but the potential across the coil is just some, let us say, 5 or 10 volt. So this 5 or 10 volt is translated to E1, and comparatively compared to E1 it is very high due to the turns ratio. Okay, now you may note one thing, that this current, the current flowing into the primary winding, okay, it is independent of the load connected here. It is actually depending upon the load on the power system. This is the power system and this is the load. So this current in the primary is being decided by the load connected to the power system. Okay, so since this is independent of the load connected here, so this current in the secondary will be simply, let us say this is I2 and this is I1. So I2 over I1 is equal to N1 over I2, N2, or I2 is just equal to N1 over I2 into I1. Since this I1 is independent of the equipment connected on the secondary side, so you can clearly see this, that the I2 is also independent of the connection on this side. Okay, now people will say, so then we can even open this point. Since it is not independent, it is not dependent on this thing, we can open also. No, we can never, or we should never open the terminals on the secondary side of a CT. Let us see why. When we draw the equivalent circuit diagram of a transformer, what we do, we show the resistance, the leakage reactance, the core loss component, the magnetization component. Okay, and this is the ideal transformer. Now when the secondary is open, then what happens? There is no current here, so there will be no reflected current here. So this current will be equal to 0, this current will be equal to 0. So any current flowing in the primary, what it will do? It will flow through the magnetization branch only. Okay, so all the current, this current is very low. All the current, this current which is in the primary is very high, independent of the equipment connected here, it is very high, so it will flow into the magnetization branch. Some will be utilized for the core loss and other will be utilized for the magnetization. So you see that if this side is open, then there will be nothing to oppose the magnetization part of this current, and this whole primary current will be utilized for the magnetization of the core only. Now you see that the core No matter how good material I use, it will get saturated at some point. Okay, so this core will get saturated and this CT will get damaged because it will go permanently into saturation. Okay, so we should never open the secondary terminals of the CT. This is one of the major precaution which we should always take. Okay, now let us try to understand various errors involved in the CT, and later on we will also see those similar errors in the potential transformer also, that we will see for CT in the next slide. Here in this slide I have drawn the equivalent circuit diagram of a normal transformer. Since CT is also a transformer, we can utilize this equivalent circuit diagram here. Okay, now here I have shown IS is the secondary side current, ZB is the burden. What is the meaning of burden? Burden is any load or any device connected on the secondary side of CT is usually called as the burden. Okay, it is usually shown in the VA, or if we know the rated secondary side current, we can also just show it in ohms also. Okay, so this is some burden, this is the secondary side current, this is the induced voltage on the secondary side, this is terminal voltage on the secondary side, this is the induced voltage on the primary side, this is IP dash, and let us say KT be the turns ratio. Okay, and this is the this no load component current. Okay, magnetization part and the loss part, the iron loss part, and this is the total primary current. This total primary current is independent of the load connected here. This is actually depending upon the power system only. Okay, now let us draw the phasor diagram for this connection. As usual, we will start from the terminal voltage on the secondary side. Although we will not use Vs after this. Okay, let us say this is Vs and this is Is, the secondary side current. So Vs plus Is into R secondary, Rs excess. This is Is excess. So this will give me Es. Okay, and I will call the angle between Es and Is as phi s. Okay, what I am doing, I am clubbing the resistance and the reactance of the winding or the leakage reactance with the burden only. Okay, and I am calling it as the secondary side power factor. Now EP will be in the same direction as Es. Okay, so flux will be lagging 90 degree. This is the flux. Okay, now there will be two components of this IO. One will be the wattful component or the loss component IW, and another will be the IM. Okay, now Is is going to have in the same direction IP dash also, and IP dash will be higher. Okay, but in the same direction. Now IP dash plus IO will give me IP. Now IO can be found out by adding IW and IM into IP dash. So this thing will give me IP. So this is IP, and the angle between IS and IP will be called as beta. Okay. Now there are two terms which we will usually use as a nomenclature in the study of the instrument transformers. Okay. First one is the nominal turns ratio. And second one is the effective turns ratio. So I will use KT for the nominal turns ratio and Kc for the effective turns ratio. Okay. So what is nominal turns ratio? It is actually the nameplate turns ratio of the equipment. Okay. So what is the nameplate turns ratio? It is nothing but the number of turns. Let us say this is N1, this is N2. So KT is usually called N2 over N1. Okay. So it is independent of the currents on the both side. It is just depending upon the construction or the manufacturing of the equipment or the transformer. However, this Kc, it depends on the current levels. Kc is usually called IP over IS. That is the effective turns ratio which we will see or observe by measuring the current on this side and this side. We don't know what is the inside construction of the city. We can only see this thing. Although it will be written on the nameplate, but we can only measure the current on this side, and we can measure only their ratio, and it will be the effective turns ratio. So ideally, what should be there? It should be there that KT is equal to Kc. Okay. But we will see that this Kc is actually a complex quantity. It is having phase as well as magnitude. Okay. So because of this Kc is usually not equal to Kt in an actual transformer. Okay. So the difference in the magnitude gives rise to the ratio error, and the difference in the angle of this give rise to the phase angle error. Okay. Now we will try to determine the expression in terms of various currents involved for these two kind of errors. Okay. That we will do in the next slide. Now let us derive the expression for the ratio as well as the phase angle. Okay. Now here we have drawn the phasor diagram. We will find first IP cos beta, then we will find IP sin beta. Okay. So this is IP, and if I extend it further such that I have a right angle here, okay, so this length will be IP cos beta. What it is equal to? It is equal to IP dash plus this length. Okay. Now this we know angle is equal to phi s. Okay. And this we know that it is equal to 90 degree. So this angle, these two angles are equal to 90 minus phi s. Okay. Now let us draw a perpendicular from this point to this point like this. Okay, so this part, since it is equal to IW, so this will be equal to IW cos phi s. So IP cos beta will be equal to IP dash plus IW cos phi s. Okay, I have got this part. Now I have to find the remaining part. Now this is IM. Let us divide this IM as IA and IB. Okay, now this is 90 degree. So this thing is equal to IA cos 90 minus phi s plus this thing is equal to IB cos 90 minus phi s. So we can see that I can write IP cos beta equals to IP dash plus IW cos phi s plus IA plus IB cos 90 minus phi s will be sin phi s. Now IA plus IB phasor sum is equal to IM. So I will write it as IM. Now this IP dash is nothing but KT times IS. Okay, so this is equation number 1, or let us say this is A. Now IP sin beta, this is IP sin beta. Okay, now I want to find this value in terms of these equation or these items. Okay, so what I will do, I will extend this line such that this joins here on the perpendicular. Okay, now you can see this line and this line are parallel. Okay, so this thing is equal to this thing. Now we know that this total part is equal to IM cos 90 minus phi s. Okay, and this part, sorry, this thing is sin 90 minus phi s. This is 90 minus phi s only. So this thing is Im sin 90 minus phi s, and this part is equal to IW sin phi s. So this thing is equal to Im sin 90 minus phi s minus IW sin phi s. Okay, so IP sin beta is equal to Im sin 90 minus phi s will be Im cos phi s minus IW sin phi s. This is equation B. Now what I will do, I will square A and square B and add them so that I will get IP out of it. So IP cos square beta plus IP sin square beta will give me IP square equals to these two squared and added Okay, so I will solve it further and just write the simplified form in the next slide. Now I have solved this or little bit expanded this and written it here. So what I need to find, I need to find the effective turns ratio. So first what I will do, I will take KT and IS common out of here. Okay. So this I omega cos phi s plus KT IS squared Im square plus I omega square or IW square. Now you see that IW square plus Im square is nothing but IO squared. So it is the magnitude of the no load component. Okay, so this is IP squared. Taking the under root on both sides, what I will have, IP over IS is equal to Kc is equal to KT 1 plus 2 KT IS Im sin phi s plus IW cos phi s plus I naught squared KT IS squared 1 by 2. Okay, now you see that KTIS is equal to IP dash. IP dash is actually quite high compared to these terms. Similarly, I naught squared is lesser than IP dash squared, very much less. So these two terms are lesser than unity. So I can expand it using binomial expression. Okay, and I will neglect the third term. So Kc is equal to KT 1 plus KT IS Im sin phi s plus IW cos phi s. Okay. Now this is some expression which I have got here. Now if I say that this angle is, let us say, zeta. Okay, or I will just say that this angle is zeta or the hysteretic angle. Okay, so I can write this as, let me erase these above three terms and I will again write it here in the next slide. Now let us see how to simplify further using the hysteretic angle. Now this hysteretic angle I have defined little bit incorrect. It is defined as the angle between the magnetization component and the no load current. Okay, so this angle, no load current IO and this IM, the angle between them is hysteretic angle zeta. So Im is nothing but I naught cos zeta and IW is I naught sin zeta. So I can write it as Kc is equal to KT 1 plus I naught sin A cos B cos A sin B. This KTIS is nothing but IP dash. Okay, so this is the expression for the effective turns ratio in terms of the nominal turns ratio, you can see that whenever this phi s, what is this phi s? Phi s is the angle of the secondary side, okay, the impedance angle of the secondary side. Whenever it is lagging, okay, then this full term is going to be positive and greater than 1, okay. So you can see that Kc will be greater than Kt whenever this load is lagging, okay. Now we will try to find the angle between them, the effective turns ratio and the nominal turns ratio, and the angle between them, this beta. So to find tangent beta, what I will do, I will divide B by A. So tangent beta will be from here, Im cos phi s minus Iw sin phi s divided by Kt Is plus Iw cos phi s plus Im sin phi s. So first let us say this equation is equation number 1, okay. Now let us say this is equation number 2. Now I can further simplify this equation, that we will do in the next slide. Now this thing can be simplified by using zeta. So Im is nothing but I naught cos zeta and it is I naught sin zeta. So tangent beta can be written as simply I naught cos of phi s plus zeta Kt Is plus I naught sin of phi s plus zeta, okay. Now you can see that this thing I naught sin phi s plus zeta is way smaller as compared to Kt Is. So I can write tangent beta as approximately equal to I naught cos phi s plus zeta over Kt Is, okay. So this is, let us say, equation number 2a. Now instead of writing this thing in this form, I can write it as Kt Is and take Kt common inside. So it will just remain Is, since Kt will be cancelled out and Kt will come here, okay. So I can write equation number 1 in this form also, Kt plus I naught by Is sin phi s plus zeta, and tangent beta is approximately equal to I naught cos phi s plus zeta over Kt Is, okay. Now this is the angle. So as long as this thing is positive, cos phi s plus zeta is positive, this tangent beta will be positive and the primary current will be lagging the secondary current, okay. However, when this thing comes negative, then we can see that beta will be negative and Ip will get shifted here and Is will be here. So primary current will be leading the secondary current in that case, okay. So depending upon phi s, since zeta is just depending upon the magnetization characteristics and the iron loss component, so we can just manipulate this thing, and by manipulating this thing we can vary the tangent beta as well as we can vary the Kc. Now in the next slide we will find two limiting values when this ratio error is 0 and when this phase angle error is 0. Let us see in the next slide. Now let us see what will happen when we have maximum effective ratio. To find that, what we will do, we will differentiate this Kc, the effective ratio, with respect to phi s. So d by Kc divided by d phi s, or the differentiation, we can see it as I naught over Is cos phi s plus zeta, and equating it to 0, what I will have, cos phi s plus zeta is equal to 0, or phi s is equal to pi by 2 minus zeta. So when phi s is equal to pi by 2 minus zeta, that is the impedance angle of the secondary side is just lesser than pi by 2 by this angle, the hysteretic angle, then what we will have maximum effective ratio. Effective will come first, maximum effective. Okay, at that time what I will have, Kc will be equal to Kt plus I naught over Is, and this phi s plus zeta will be equal to pi by 2. Okay, so this is the maximum value. Now at this point what will be the phase angle? This tangent beta will be equal to this cos phi s plus zeta will be equal to 0, so it will be equal to 0, so beta will be equal to 0. So at maximum effective ratio I will have phase angle error equal to 0. Okay, now what will happen when this phi s is very small, or let us say equal to 0, that is the secondary side of CT is not giving load to any trip coil etc, that is it is just giving a resistive burden. Okay, so what will happen in that case? We can see that Kc will be equal to Kt plus I naught sin zeta. Now I naught sin zeta is nothing but IW, the loss component of the no load current, over Is, and the phase angle error will be equal to I naught cos zeta equal to Ic or Im Kt Is. Okay, so you can see that when the burden is resistive, then the ratio error is being determined by the watt-full component, that is the loss component of the no load current, and the angular or the phase error is being determined by the magnetization part of the no load current. Okay, now this actually phi s keeps on varying depending upon the type of equipment connected to the secondary side, depending upon various system to system. Okay, so we cannot have any fixed guideline that what will be the value of phi s, but usually it is lagging whenever the secondary circuit is giving current to the trip coil of the breaker, because the trip coil will be inductive in nature. Okay, now you see that when we are having phi s as pi by 2 minus zeta, that is it is quite lagging in nature. Okay, then this Kc is equal to Kt plus I naught over Is. Okay, so effective turns ratio Kc is greater than Kt. So what we will do to compensate this error, what we will do, let us say the CT is having 2:200 ratio. What I will do, I will just reduce the number of turns on the secondary side. Let us say I will do it 198. So what will happen? This Kc was greater than Kt. Okay, so this thing, the error part, if I say Kc minus Kt over Kt is equal to I naught Kt Is. Okay, so this thing, what will happen? If I reduce the number of turns, this Kt will be reduced. So when this Kt is reduced, let us see what will happen. This is reduced. Now this is I naught over Is. This Is can be written as IP dash over IS is equal to KT. So IS can be written as KT over or IP dash over KT. Over KT. So this Kc which got increased due to the error part, now on reducing the number of turns, this Kt is reduced, this again is also reduced, then, and this is independent because it is depending on the power system only, then ultimately this Kc will again come towards the required nameplate turns ratio. However, the turns ratio practically will be reduced, but the Kc will come near to the nameplate turns ratio which we actually require in the power system. Okay, so in this way we will be able to reduce the ratio error. Okay, so this is the one thing, how to reduce the ratio error by the turns compensation. Okay, now the other thing is how to compensate for the phase angle error. Then we can clearly see that this can be covered just by changing the power factor of the secondary side. Okay, since by varying this phi s, let us see from 2a, I can get beta from positive to negative to 0. Okay, so I can reduce this, but there is a drawback in that by controlling this I am losing the control on the effective turns ratio. So these are the two parts of a double-edged sword. Okay, however, in the current measurement we usually have to consider more deliberately the ratio part instead of the angular part. So the phase angle error is not that much important in terms of its utilization. Okay, so we try to reduce the ratio error in the CT. Now I will leave you with a homework to find d by d phi s or of tangent beta from equation number 2 and then equate it to 0. Then find the condition for beta. Now in the next video we will try to find the transient response or the response of the CT during transients of the power system, and we will see what happens during the transient, what should we do to reduce the effect of transient so that the CT faithfully transform the values during the initiation of the or the first few seconds of or first few milliseconds of the fault. Okay, so if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.